Welcome to another deep dive.
Yeah, glad to be here.
Whether you are, catching up on the absolute latest breakthroughs in neuroscience, or maybe you are prepping for a high-stakes presentation in a biology seminar, or perhaps you are just intensely, undeniably curious about how the human body actually works behind the scenes, you are in exactly the right place.
Absolutely.
Because this specific deep dive is custom tailored for you. Today, we are taking an incredibly intricate, um, totally fascinating journey into the neuroscience of pregnancy.
And it is a wild journey.
It really is. But we aren't just looking at general biology or, typical hormonal swings. We are zeroing in on a very specific, highly complex phenomenon.
Mm.
We're looking at how pregnancy literally re-engineers the human brain's reward system.
Right. The literal hardware of the brain.
Exactly. We are going to track these staggering physical and chemical changes from the very moment of conception all the way through the first 2 years of a child's life.
Which is a critical window.
And just to set expectations for you listening, that 2-year mark happens to be the furthest extent of the longitudinal data available in our current stack of sources, though the implications stretch out much, much further.
They absolutely do. Decades further, really.
Speaking of those sources, we are looking at a highly curated collection of high-impact scientific papers. We pulled these directly from top-tier journals. We've got everything from the foundational paradigm-shifting studies of 2009 right up to the absolute cutting-edge, state-of-the-art research just published in 2024 and 2025.
The new data is it's incredible.
Okay, let's unpack this. Because the sheer scale of what happens to the architecture of a pregnant brain is mind-blowing. And frankly, it's an area of science that was overlooked for far too long.
Oh, without a doubt. It really was treated as a footnote in neurology for decades. It was largely relegated to obstetrics rather than neuroscience.
Right, like it was just a localized physical event.
Exactly.
Yeah.
But to understand the true scale of this neurological event, we have to establish a foundational concept right out of the gate. In the scientific community, we now refer to this period of life as matrescence.
Matrescence, like adolescence.
You hit the nail on the head. If you want a mental model for matrescence, you can think of it as a developmental window of neurobehavioral plasticity that is completely on par with adolescence.
Wow.
When we think of a teenager, we culturally understand that their brain is undergoing massive, chaotic restructuring to prepare them for adulthood. The exact same level of profound structural change, the significant network connectivity shifts, and major regional activation adjustments are happening in a mother's brain.
That is so wild to think about.
And the overarching theme here, the biological imperative driving all this really expensive metabolic remodeling, is survival. The maternal brain is physically tearing itself down and building itself back up to ensure the survival of the infant.
That comparison to adolescence is so helpful because it frames pregnancy not just as a temporary 9-month state of being uncomfortable or hormonal, but as a permanent developmental milestone.
Right, you don't go backwards.
Exactly. Don't go backwards after adolescence. You don't go backwards after matrescence. But to actually see how this happens in real time, how the brain remodels itself, we need to talk about the methodology of these new studies.
There is a paper from 2024 that just blew the doors off this topic.
Yes. We are looking at a landmark paper by Pritchett and colleagues. It was published in the journal Nature Neuroscience. The title is Neuroanatomical Changes Observed Over the Course of a Human Pregnancy.
Nature Neuroscience 2024.
That's the one. And what separates this from historical research is the approach. Previously, you might scan a group of 50 women before they got pregnant, and then scan them again 6 months after they delivered.
Right, a before and after picture.
Exactly. You'd compare the two static snapshots and try to guess what happened in the middle. But the 2024 Pritchett study utilized a methodology called dense sampling. Wait, dense sampling? Does that mean what I think it means? Like, they didn't just take snapshots, they essentially took a video.
That is a great way to visualize it. Instead of scanning a massive cohort of different people once or twice, the researchers mapped a single individual with incredible frequency.
A single person.
Yes. They performed high-resolution brain scans starting from the preconception phase, continuing all the way through gestation week by week, and then kept scanning her continuously up to 2 years postpartum.
That is dedication.
They captured 26 separate MRI scans of the exact same brain over the entire duration. It provides eye-resolution, chronological map of the brain as it morphs. It is essentially a stop-motion film of matrescence in action.
I just want you, the listener, to imagine the sheer dedication that takes. Getting into an MRI machine is not a casual afternoon activity.
No, it is not.
It's loud, it's claustrophobic, and doing that week after week while heavily pregnant is a monumental contribution to science. And the plot of that stop-motion film they captured is totally unexpected.
Hmm.
Because when you think of the brain preparing for something as monumental as motherhood, you logically assume it's growing.
Right, you assume more is more.
You assume it's getting bigger, adding tissue, building new processing centers to handle the workload. But the Pritchett paper shows the exact opposite.
The exact opposite.
As the gestational weeks progressed, they observed pronounced, undeniable decreases in gray matter volume, what researchers call GMV, and decreases in overall cortical thickness across the brain.
Yeah, the cortical tissue, which is the intricately folded outer layer of the brain where complex higher-order processing happens, is physically reducing in volume. It's shrinking.
It's shrinking. That sounds alarming at first.
It does. But if we look closer at the imaging, we see that is only half of the story. While the gray matter is decreasing, the white matter is undergoing a totally different transformation. Through advanced imaging techniques, specifically correlational tritography analyses, the researchers found nonlinear increases in white matter quantitative anisotropy, or QA, throughout the first and second trimesters.
Okay, hold on. We need to translate that for a second. Quantitative anisotropy QA ball. What are we actually looking at when we measure that? Are we basically saying they measured how well paved the neural highways are?
That is a perfect analogy, actually. White matter is essentially the vast network of communication cables connecting the different gray matter processing centers of the brain.
The cables.
Yes. Quantitative anisotropy is a mathematical measure of the microstructural integrity and directional flow of those white matter tracks. Higher QA means the water molecules in the brain are flowing smoothly and directly along these tracks. It indicates highly efficient, tightly bundled nerve fibers.
So a higher QA is a good thing.
A very good thing. So when the researchers saw QA increasing dramatically in the first and second trimesters, they were watching the integrity and efficiency of these neural superhighways being heavily reinforced. The communication lines across the brain were being optimized for speed.
So the gray matter processing centers are literally shrinking, but the white matter cables connecting them are getting stronger and faster.
Exactly.
It's a massive architectural renovation. They are knocking down walls, but upgrading the internet speed.
That is exactly what's happening.
And there's another physical change happening alongside this that I found really curious in the paper. The study highlighted a significant increase in the volume of the brain's ventricles, as well as an increase in cerebrospinal fluid, or CSF.
Right. And the interpretation of the cerebrospinal fluid changes requires some nuance. The ventricles are the fluid-filled cavities in the center of the brain. On one hand, the expansion of these ventricles and the overall increase in CSF could partially reflect the profound physiological adaptations of pregnancy. Pregnant bodies retain a massive amount of water, blood volume increases significantly.
Oh, sure.
And this might cause a temporary compression of the cortical tissue, making it appear thinner while the fluid spaces expand. However, the longitudinal data, remember, they tracked this woman for 2 years after birth, tells us it's not just temporary water weight pushing against the brain.
Right, because if it was just swelling from water retention, the brain would snap back to normal like a rubber band a few weeks after delivery. But it doesn't.
Exactly the opposite. The endurance of these structural changes points to underlying permanent cellular alterations. While the researchers acknowledge the role of fluid dynamics, the prevailing consensus is that we are looking at actual remodeling of glial cells.
Glial cells being the support system.
Yes, the crucial cells that support, feed, and protect neurons, as well as changes in myelination. Myelin is the fatty insulation wrapping around those white matter tracks. Thicker insulation means faster electrical signals.
And the timeline of the rebound really proves this. The study shows that the white matter QA, that superhighway integrity we talked about, actually peaks during pregnancy and then fully returns to its baseline pre-pregnancy levels by the very first postpartum scan.
Right.
The highways get paved for the main event, and then the construction crews go home. But the decreases in gray matter volume, those persist. Even at the 2-year postpartum mark, there is only a very modest rebound in gray matter. The gray matter does not grow back to its original size.
If we connect this to the bigger picture, this dense sampling methodology provides a profound revelation for neuroscience. By mapping this chronological timeline through the first 2 years of the child's life, the data proves definitively that pregnancy brain is not just a 9-month hormonal fog that lifts after you deliver.
It's permanent.
It is a multi-year neuroarchitectural shift. The brain you have when you enter pregnancy is structurally fundamentally different from the brain you have 2 years after giving birth.
Which sets up our next major point perfectly. Because right now, you listening to this might be thinking, wait, the part of my brain responsible for complex thought is physically shrinking, and it doesn't grow back.
It sounds bad.
It sounds terrible. It sounds like a neurological deficit. But here's where it gets really interesting. Losing brain volume in this specific context is actually an incredibly sophisticated evolutionary optimization process.
It's a feature, not a bug.
Exactly. It's a biological phenomenon known as synaptic pruning. To unpack this, we are pulling from a brilliant 2022 paper by Pulaski and colleagues. It's titled, "Less Can Be More: Fine-Tuning the Maternal Brain," published in Neuroscience and Biobehavioral Reviews.
A fantastic paper.
And we are pairing that alongside a comprehensive 2024 systematic review by Eunice. Both of these sources argue forcefully that this loss of physical volume is actually a massive gain in processing efficiency.
Less is more is the perfect conceptual framework here. To truly grasp how this pruning works, we look to another landmark paper, this one from 2016 by Hoek-Sima and colleagues,
Right.
titled "Pregnancy Leads to Long-Lasting Changes in Human Brain Structure," also published in Nature Neuroscience. They mapped these gray matter reductions and discovered they are not happening randomly across the cortex. The volume loss highly selectively targets very specific regions of the brain.
It's targeted.
Highly targeted, specifically regions that subserve social cognition. These are the intricate neural networks responsible for our ability to interact with others, to decode complex social cues, and to process interpersonal dynamics.
I always think of synaptic pruning like trimming a bonsai tree. You cut away the excess tangled branches so the ones that remain can grow stronger, more directed, and more resilient.
That's a beautiful way to think of it.
But the big question is, why social cognition? Why is the brain deliberately pruning away the networks we use to navigate the world? What is the specific goal of targeting those exact regions?
The goal is extreme, laser-focused specialization. Human babies are born incredibly altricial,
Altricial, meaning dependent.
meaning they are completely helpless compared to almost every other mammal on Earth. A baby horse can run a few hours after birth. A human baby cannot even hold its own head up for months.
True.
They require intense, constant, hypervigilant care. By selectively fine-tuning these social cognition networks, the brain drastically enhances the mother's ability to empathize. It improves her ability to recognize subtle, fleeting facial expressions and emotions. And crucially, it sharpens what psychologists call theory of mind regarding her baby.
Theory of mind, so the ability to project into someone else's headspace and guess what they're thinking or feeling.
Exactly.
Which is pretty critical when you were dealing with a tiny human who cannot speak.
It is the difference between life and death for the infant. The mother needs to be able to infer the mental state, the immediate needs, and the distress levels of her baby based entirely on nonverbal cues. A specific type of cry, a slight shift in posture, a change in breathing. The brain is literally cutting away the noise. Perhaps the complex, energy-draining neural pathways used to navigate office politics or distant social circles.
Right, you don't need to worry about the office when you have a newborn.
Exactly. It cuts that away to focus entirely, efficiently, and flawlessly on the signal of the baby. The gray matter is thinner because it is more streamlined.
And when we say this is a long-lasting change, we aren't just talking about the toddler years. There is a specific data point in the 2022 Pulaski paper that absolutely stopped me in my tracks.
I know the one you mean.
The researchers referenced neuroimaging studies looking at healthy older women with an average age of 73. And they found that women who had given birth and raised children still had a noticeably thinner left dorsolateral prefrontal cortex.
The DLPFC.
Yes, the DLPFC, as well as a thinner right paracalcarine sulcus compared to women of the exact same age who had never had children.
That's astounding.
The structural changes that occur during a single pregnancy leave a permanent, visible signature on the brain that lasts an entire lifetime. A neuroscientist could look at a scan of a 70-year-old brain and tell if that person had ever been a mother.
It is a remarkable testament to the enduring, monumental impact of matrescence. The brain never fully reverts. And while this cortical pruning in the gray matter is optimizing the brain for empathy and social processing, it is only one piece of the puzzle.
Just one piece.
There's another system, located much deeper in the evolutionary core of the brain, that is simultaneously being supercharged. Because all the empathy in the world doesn't matter if you don't have the drive to actually perform the exhausting labor of caregiving.
And it is exhausting.
This brings us to the core neurobiology of maternal motivation.
Yes, this is the transition to the absolute star of the show for today's deep dive, the brain's reward system. We've talked about the gray matter shrinking to focus the mind, but now we need to talk about the engine.
The engine of motherhood.
What actually drives a mother to get out of a warm bed at 3 a.m. day after day, month after month, to soothe a screaming infant?
To map out the plumbing and the wiring of this maternal motivation system, we draw heavily on two highly influential papers. The 2016 paper by Kim and Strathern, Oxytocin and Maternal Brain Plasticity, published in New Directions for Child and Adolescent Development.
Okay.
And the 2015 paper by Feldman, The Adaptive Human Parental Brain, from Trends in Cognitive Sciences. The neurobiology they detail is elegant, primal, and incredibly powerful. It all starts with a specific tiny trigger region deep in the brain called the medial preoptic area, or the MPOA.
MPOA.
Yes, the MPOA is located in the rostral hypothalamus.
Okay, the MPOA, let's call that the brain's ignition switch for motherhood. So the switch gets flipped. Where does the electrical signal go from there?
The MPOA projects its signals directly into the brain's mesolimbic dopamine circuits. Specifically, it sends dense neural projections down to a region called the ventral tegmental area, known as the VTA.
VTA, got it.
From the VTA, the pathway continues into the nucleus accumbens, or the NAC, which is nestled in a region called the ventral striatum. This entire pathway from the MPOA ignition switch down to the VTA and up into the ANAC is the brain's primary foundational reward circuit.
It's the dopamine highway.
Exactly. It is the exact same circuitry that processes the intensely rewarding feelings we get from eating delicious, high-calorie food, or the rush of winning a gamble, or the intoxicating feeling of falling in love.
And what happens when the MPOA sends its signal down into this specific, highly sensitive reward circuit?
The result is a massive, localized release of dopamine into this pathway. This dopamine flood radically enhances the perceived appetitive value of the infant.
Appetitive.
Appetitive in neuroscience means it drives a desire to approach and consume, or in this case, approach and care for. Suddenly simply interacting with the baby, smelling the top of the baby's head, hearing the baby coo, all of these mundane sensory inputs become intensely, overwhelmingly rewarding stimuli on a deeply neurological level.
That's incredible.
The brain is chemically bribing the mother to interact with the child.
But dopamine isn't acting alone here, is it? Because we all know dopamine can be fleeting. It spikes and then it crashes. To sustain this drive for years, we have to bring in the ultimate neuromodulator.
Oh, absolutely.
I'm looking at the 2010 paper by Galbali and colleagues, The Role of Oxytocin in Mother-Infant Relations. Oxytocin is famously, almost colloquially, known as the love hormone or the cuddle chemical.
We hear that all the time.
Right. But structurally, mechanically, what is it actually doing inside this specific dopamine reward loop?
Oxytocin is produced directly in the hypothalamus, right near our ignition switch, the MPOA. In this context, oxytocin acts as the master conductor for the entire motivation system.
The conductor.
Yes. It travels down and acts directly on the ventral tegmental area, the VTA. Its job is to actively facilitate and amplify the release of dopamine into the nucleus accumbens. Oxytocin primes the pump.
So it makes the dopamine hit even stronger.
Much stronger. Without oxytocin continuously modulating and lubricating the circuit, the dopamine response wouldn't be nearly as robust. Furthermore, oxytocin tightly links that dopamine reward specifically to the infant's unique sensory cues.
Oh, wow.
It ensures the mother finds her baby rewarding, not just any baby.
And the plumbing doesn't just stop at the reward centers. The 2015 Feldman paper notes that the amygdala is also receiving signals from the MPOA.
Right.
For anyone who isn't familiar, the amygdala is the brain's emotional processing center. It's heavily involved in fear, threat detection, and the fight-or-flight response. Why is the fear center getting wired into the maternal care system?
Because keeping a baby alive requires a healthy dose of paranoia.
Ah, so true.
The amygdala receives direct projections from the MPOA, which significantly increases maternal vigilance. The mother becomes exquisitely attuned to potential threats in the environment. Furthermore, the researchers found that oxytocin actually creates new synaptic plasticity within the pathways of the amygdala.
So oxytocin is rewiring the fear center too.
Exactly. This oxytocin-primed plasticity augments the salience or the absolute biological importance of the infant's bonding cues. The brain is running a dual operation. It is simultaneously making the baby the most chemically rewarding thing in the environment while structurally altering the fear center to make the mother highly vigilant and emotionally reactive to any distress signals the baby might send out.
Love and fear.
Love and fear wired together by oxytocin.
I want you, the listener, to just pause for a second and imagine how unbelievably powerful a biological drive has to be to override your most basic primal survival instincts. Every animal is wired to prioritize sleep, to prioritize food, to avoid pain, and to seek personal comfort.
It's fundamental biology.
Yet this system has to convince a human being to sacrifice all of those things for months and years on end. This specific pathway, the MPOA sending signals to the VTA, releasing a flood of dopamine into the NAC, all heavily modulated oxytocin and wired into the amygdala's threat system that is the literal physical engine of maternal motivation.
It is the biological failsafe for the continuation of the human species. And what is truly fascinating about modern neuroscience is that we don't just have to theorize about this invisible circuit based on animal models anymore. We possess the technology to actually watch it fire in living human beings.
Yes. Okay, so we know the plumbing and the wiring are there. But seeing a diagram of wires is very different from watching the electricity flow in real time. Have researchers actually caught this happening live?
They have.
We are moving from static anatomical imaging to functional MRI, or fMRI. We're looking at the 2015 paper by Swain, The Human Parental Brain, in vivo neuroimaging, published in Progress in Neuropsychopharmacology and Biological Psychiatry.
The Swain paper provides a beautiful overview of how researchers use fMRI to watch the maternal brain react. They place a mother inside the scanner and present her with very specific visual and auditory stimuli.
Like what kind of stimuli?
Like flashing a picture of her own baby on a screen, or playing an audio clip of her baby crying over a set of headphones. What these in vivo studies consistently reveal is that these cues trigger a massive, synchronized network.
A whole network firing at once.
Yes. You see simultaneous activation in the cortical regulation regions. These are the areas up in the prefrontal cortex dealing with complex thought, planning, and emotional regulation. But simultaneously, you see hyperactivation deep down in those subcortical drive regions we just discussed.
Reward centers.
Exactly. The basal ganglia, the thalamus, and the substantia nigra, which are all incredibly rich in dopamine receptors. The thinking brain and the feeling brain fire together.
To really see the nuance of this in action, we have to dive deep into an absolute landmark fMRI study from 2009. This is the paper by Strathern and colleagues.
Oh, this is a brilliant study.
It really is. It's titled Adult Attachment Predicts Maternal Brain and Oxytocin Response to Infant Cues, published in Neuropsychopharmacology. The setup for this experiment is incredible and really clever. They recruited 30 first-time mothers and placed them in an fMRI scanner at exactly 11 months postpartum.
11 months, so well into the caregiving phase.
Right. While lying perfectly still inside the scanner, the mothers were shown a rapid series of baby faces on a screen. Some of the faces were unknown infants, random babies they had never seen before, but intermixed randomly were pictures of their own infant.
Right.
And to add another layer of complexity, the faces displayed different emotions: smiling, neutral, and crying.
The resulting data from those functional scans yielded spectacular insights. The researchers found that when a mother was viewing her own infant's happy, smiling face as opposed to an unknown infant's face, those key dopamine reward regions we highlighted earlier lit up like fireworks on the scan.
Fireworks.
They recorded massive, statistically significant activation in the substantia nigra, the dorsal putamen, and the ventral striatum. The brain was providing a massive, highly localized chemical reward signal in direct response to the specific visual cue of her own child expressing joy.
So what does this all mean? Fundamentally, it proves the biological premise. The brain is hardwired to make caregiving feel good. It rewards the mother for successfully making the baby happy.
Exactly.
But the Strathern study didn't just stop at mapping the average response. They looked at the individual differences between the mothers. Specifically, they focused on their attachment styles.
This is where it gets incredibly deep.
Months earlier, before the babies were even born, the researchers conducted in-depth psychological interviews to assess each woman's own attachment history, essentially how they relate to others based on how they were parented themselves. They divided the mothers into two broad categories: those with a secure attachment style and those with an insecure or dismissing attachment style.
And the differences in how those two groups of brains fired inside the scanner were staggering. Mothers who had been classified as having a secure attachment style showed significantly greater, more robust activation in the ventral striatum and the hypothalamus pituitary region when viewing their own baby's face.
The hypothalamus.
Now remember, the hypothalamus is exactly where oxytocin is produced, so their reward and bonding centers were firing much harder. But the researchers went a step further. They had also measured the mother's peripheral oxytocin levels in their blood during a separate physical play session with their babies at 7 months postpartum.
Real-world blood tests.
Yes, the securely attached mothers had much higher oxytocin responses during actual physical play. And crucially, those peripheral blood oxytocin levels positively correlated with the degree of brain activation seen months later in the fMRI. It was a perfect, measurable alignment of brain activation and peripheral hormonal response.
That is the picture of a smoothly operating, highly efficient maternal reward system. But then we look at the data for the mothers classified as having an insecure dismissing attachment style. And the neural response is completely different. It's almost chilling.
It's a profound difference.
When these insecurely attached mothers viewed their own infants' sad or crying faces, their reward centers didn't light up to drive a soothing approach. Instead, their fMRI scans showed much greater activation in two very specific, very different areas of the brain: the anterior insula and the dorsolateral prefrontal cortex, which we called the DLPFC earlier.
This raises an important question about how our brains process negative social cues and what those specific regions do. The anterior insula is a region of the brain strongly associated with processing feelings of unfairness, physical pain, and even visceral disgust.
Pain and disgust.
Yes. The dorsolateral prefrontal cortex, on the other hand, is heavily associated with intense cognitive control, executive function, and the active suppression of emotion. It's the brain's brake pedal.
The brake pedal. So neurologically speaking, when an insecure or dismissing mother sees her own baby crying, her brain is not automatically triggering a reward-based, oxytocin-fueled approach mechanism to comfort the child.
No, it's not.
Instead, her brain is signaling a negative, almost painful, affective state via the insula, coupled with a high degree of cognitive effort from the DLPFC to control or actively suppress that negative emotional response.
It's working overtime to manage the distress.
It is profound. I mean, it is the literal neurobiology of transgenerational trauma. Or on the flip side, transgenerational security. It shows that a mother's own psychological history, the attachment style she developed throughout her entire life based on her own childhood experiences, physically alters the structural firing of her brain's reward system when she looks at her own child.
That's a powerful way to put it.
Your past experiences dictate which network of neurons fires when your baby cries. But the incredible thing about the brain is that it isn't set in stone. The postpartum period itself offers a massive window for new growth.
That is a crucial point. The brain doesn't just change during the 9 months of pregnancy and then lock into a permanent, static state the moment the baby is born. The postpartum trajectory is an entirely distinct, highly active phase of neuroplasticity. The architecture is still moving.
Right, let's look at this early postpartum growth phase. We're pulling data from the 2010 paper by Kim et al., The Plasticity of Human Maternal Brain, published in Behavioral Neuroscience, and pairing it with a fantastic 2020 paper by Luter et al. From the journal Cortex titled From Baby Brain to Mommy Brain, Widespread Gray Matter Gain After Giving Birth.
Excellent papers.
Now, we established very clearly earlier that during pregnancy, the overall gray matter volume shrinks due to pruning. But these specific papers show that in the immediate postpartum period, if you look at the scans from weeks 2 to 4 and compare them to scans taken at months 3 to 4 postpartum, there are actual measurable increases in gray matter volume.
Increased?
Yes. The brain starts aggressively building back up in specific areas: the prefrontal cortex, the parietal lobes, and those critical midbrain reward areas we've been obsessing over, like the hypothalamus, the substantia nigra, and the amygdala.
To understand this fundamental shift from the shrinking phase of pregnancy to the growing phase of the postpartum period, we rely on a brilliant framework established in the 2018 paper by Muller, titled Brain Plasticity in Pregnancy and the Postpartum Period.
Okay, what does Muller say?
Muller distinguishes between the drivers of these two phases. The plasticity, the structural changes we see during pregnancy, is primarily what we call hormone-derived.
Hormone-derived.
Yes.
Yeah.
It is driven by the massive, historically unprecedented physiological surges in estrogen and progesterone coursing through the pregnant body. Those hormones are the demolition crew and the architects. However, the plasticity we see in the postpartum period is fundamentally different. It is experience-dependent.
Experience-dependent, meaning the actual physical, daily act of mothering is what is driving the brain to grow new tissue.
Exactly that. The sensory inputs are driving the structural outputs. The physical interaction with the infant, the constant tactile stimulation of holding them, the neurochemical act of suckling during breastfeeding, the intense sleep deprivation, the endless behavioral adaptation of learning to interpret and soothe a cry.
It's constant input.
Endless input. All of these intense, repetitive sensory and behavioral experiences are demanding more processing power. The brain responds to this demand by literally growing new volumetric connections in the prefrontal cortex and midbrain. The daily repetition of caregiving builds the brain.
And we have brand new state-of-the-art evidence from 2025 that maps exactly how the lingering hormones from pregnancy interact with this new experience-dependent phase to build that tissue.
It's fascinating research.
The 2025 paper by Chechko and Niels, published in Translational Psychiatry, titled From Pregnancy to Postpartum, The Dynamic Reorganization of the Maternal Brain. It provides the missing link we've been looking for.
The Chechko and Niels paper is a masterpiece of correlational neuroscience, because it links precise hormonal environments with subsequent brain volume. They discovered that gradually increasing blood progesterone levels during the postpartum period closely correlate with the temporal patterns of postpartum gray matter changes.
And the networks.
Yes, and the reorganization of resting state connectivity networks. Even more incredibly, they found a predictive link. They measured a mother's urine estradiol levels back in her third trimester of pregnancy. They found that those specific third trimester levels mapped directly onto and predicted the amount of gray matter changes observed 1 to 4 months after she gave birth.
Wait, so the hormone levels before birth predicted the brain growth after birth?
Exactly. The hormonal environment of late pregnancy casts a long shadow. It essentially sets the stage and primes the tissue for the physical remodeling that the behavioral experiences will trigger months later.
And the most important part of the Chechko paper is that it ties all of this dense neuroanatomy and endocrinology back to actual real-world human behavior, because why does this growth matter?
Right. They found that these specific volumetric changes in the postpartum period, specifically the measurable growth in the amygdala, the thalamus, and the anterior cingulate cortex, actually predicted less hostile behavior toward the child as they grew older.
It's a direct correlation.
Let me repeat that. The more the brain successfully rebuilt and restructured itself in these specific emotional regulation and reward regions during those early months, the more patient, the more attuned, and the less hostile the mother was in her actual parenting behavior later on.
It perfectly, elegantly ties together structure, hormones, and behavior into one cohesive narrative. And on a deeply human level, it validates the immense psychological, emotional, and physical shifts that mothers experience.
It proves it's not just in their heads, ironically.
Exactly. When a mother tells you she feels fundamentally changed by the experience of having a child, she is not just experiencing a psychological shift in identity or a change in her daily routine. She's experiencing a literal, physical, measurable rewiring of her central neuroanatomy. Her brain is not the same organ it was before conception. So to recap this incredible, truly wild journey we've been on today, we started by looking at the global, dense sampled mapping of the brain, witnessing the profound bonsai tree pruning of the cortical gray matter to eliminate social noise, while the white matter integrity spiked to build hyperfast neural superhighways.
Right?
We then dove deep into the plumbing of the mesolimbic dopamine reward system, tracing the exact path from the mTOA ignition switch to the VTA down to the NAC, and saw how the master conductor, oxytocin, forces the brain to find the baby rewarding while keeping the amygdala hypervigilant.
The perfect balance of love and fear.
We tracked how a mother's own lifelong attachment style dictates whether that reward system fires with joy in the ventral striatum or whether the insula fires with pain and distress. And finally, we saw how the brain shifts gears and continues to physically morph, rebuild, and add volume through the first 2 years of the child's life.
Driven by hormones and experience.
Exactly. Driven by a complex, beautiful dance of lingering pregnancy hormones and the intense, relentless daily physical experience of caregiving. I want to remind you, the listener, the next time you think about biology, that your brain is not a static organ sitting in a jar.
Far from it.
It is a remarkably dynamic, responsive structure. It's capable of physically tearing down and reshaping its own architecture to accommodate the single most demanding, exhausting, and important social task in human existence: keeping a child alive and keeping them loved.
And as we've seen from the longitudinal data,
Yeah.
those structural changes are so profound, so deeply etched into the neural pathways, that they leave a recognizable permanent footprint on the brain well into a woman's 70s and beyond. It's a lifelong neurological signature of caregiving.
Which leaves us with a final, lingering, provocative thought for you to mull over and explore on your own long after this deep dive ends. We've established this incredibly powerful concept of experience-dependent plasticity, the proven idea that the immense physical and emotional act of interacting with, soothing, and caring for an infant actively rebuilds the midbrain and prefrontal cortex.
Right.
We've seen that the biological act of pregnancy, combined with the behavioral act of caregiving, leaves this permanent signature on the brain's reward and social cognition networks. But what happens outside the bounds of biological motherhood?
Ah, that is a fascinating question.
Does extreme, intense, long-term caregiving in entirely non-biological contexts, such as adopting a child and raising them from infancy with that same level of hypervigilance, or perhaps dedicating decades of your life to round-the-clock care for a severely sick spouse,
Yeah.
does that level of relentless, love-driven, experience-dependent caregiving eventually forge the exact same permanent neuroanatomical pathways in the brain?
It's entirely possible based on the mechanism.
Does love build the same house, even without the hormonal architects? Thank you so much for joining us on this deep dive into the source material. Catch you next time.